Now, more generally, you don't have to have a line segment, right? So what's actually going on in general? I'd like to attempt to anyway draw a picture of what's going on in general. And so you don't need a line segment. I mean, if you have one, great. That's easier to deal with. But the power of what we're trying to build up to and do is you can have any curve you want. So maybe from here to there, and let's say the curve travels, start here, end at this point there, and you travel along this way, and this curve, I guess it's in this section, it's a line, but it's this curve is what we travel along, and there's we're going to talk about the integral over this curve. Okay, if you travel along here and pick up for each xy along here, you run through the function f and you pick up a z value. So what's going on? We're going to attempt to draw a 3D picture. X-axis, y-axis, z-axis. So let me try to draw this same curve. Let's see. So from a point kind of like there, we travel mostly increasing the y value. So like, I think like this. Forgive me if this is not perfect. It's not going to be perfect. Okay, so we travel along this way. And then up above, there's the graph of a function, whatever function you have. Right? It looks like a surface. It looks like you wave a towel in freeze frame here, right? So this is your z is equal to f of x comma y. And then the point is that, I don't know if I'm going to survive drawing this, but like above here, there's, so this point directly above. Now the height, it just, where you get to, it just depends, And then from this point here, you travel up and you might get to right here. I mean, these two green dots don't have to be at the same height. It's just wherever they end up. And so each of these points down here are at the same height because z is 0. But then all along here, these points in green that are all above these points down here, these points in green up on the surface, they don't have to be at the same height, but they were going to form a curtain. A curtain. So the exact area, what we're finding with this line integral, we're going to integrate this function, whose graph looks like this, over this curve here, this cinnamon roll, or whatever. And this exact area is actually going to be the limit as n approaches infinity of the sum I goes from 1 to n of f of xi star yi star times delta s sub I. The way that we will notationally write this, though, is integral over the line c, or the curve c, capital C, of f of x comma y ds. ds just to mimic delta s there. And then, cool, this is the definition. This is the thing we're trying to define, all right? Here's how it's computed if you do Riemann-based things and take a limit. But the way we're actually going to compute it, so what we're talking about here is to actually compute. What you do is you do an integral from a to b of f of x of t comma y of t times square root of dx over dt squared plus dy over dt squared dt. So this is super useful. This is practical. This is helpful to, I mean, I know this is a little weird, but just seeing this helps us gain an appreciation and an understanding for what we were doing back here. This is the notation you're going to see a lot, but you've got to convert that to this in order to practically compute. There's a lot to say. How do we compute what's going on? Where the heck did the x of t, y of t, dx dt, where did all these things come from? What you actually have to do is note that x of t, y of t, and then those values a and b, those are, of course, t values. So t goes from a to b. What does this look like? I hope you're saying to yourself, this looks like a parameterization. And specifically, it's a parameterization of the curve C. Also, this part right here, let me circle it maybe in blue, ds is root dx over dt squared plus dy over dt quantity squared dt. So we've actually seen this before. It's actually called the arc length differential. So if you look at the arc length, yeah, don't worry about the naming too much, but if you look at the formula for arc length, there's a thingy that looked like this in it. Okay, so we'll stop this section here.